Start.
Thank you very much. I'm Shinichiro Matsuo from Nagoya University. And today, the title of my talk is Analytic Indices in Lattice Gauge Theory and Their Continuous Limits. And first of all, I'd like to thank the organizer, Professor Hayashi, for giving me this opportunity. Thank you very much. Thank you very much. I'm Shinichiro Matsuo from Nagoya University. And now let's start. And this talk is based on joint work with many people. Joint work with Hidenori Fukaya, from Osaka University, and Mikio Furuta from Tokyo University of Tokyo, and Tetsuya Onogi from Osaka University, and Satoshi Yamaguchi. He is also in Osaka, and Mayuko Yamashita. She is in Kyoto, RIMS. And this is based on joint work with these 5 peoples. And Fukaya and Onogi and Yamaguchi are physicists. And Furuta and Yamashita, including me, are mathematicians. So this talk is based on happy collaboration with 3 physicists and 3 mathematicians. And now the paper is now in preparation, and it will appear on the archive next month, I hope. So let's get started. Let me first describe our main result before going into details. So let me start main theory. So everything will be explained later. But anyway, fix a smooth connection A on a torus TD for d greater than or equal to 0, and for any sufficiently fine lattice approximation of A and T, TD, we have the equality of the spectral flow of the Wilson-Dirac operators on the lattice. And it is equal to the analytic index of usual Dirac operator on the torus. And moreover, we have the same is true for these indices over family case. Homogeneous Clifford indexes. This is the main theorem. So our theorem is concerned about lattice gauge theory, and the lattice approximation of analytic index fundamental invariance of Dirac operator can be computed from lattice approximation Wilson Dirac operators. This is the main theorem. And I'd like to explain this about this theorem in this talk. Okay. And as I said to you, this is a theorem about lattice gauge theory, but my motivation comes from topology. So before going into the detail of this theorem, let me tell you my motivation. In short, my motivation comes from topology, especially four-dimensional topology. And so let me explain something about topology. The fundamental problem in topology is the classification problem. That is, classify all the manifolds in given dimension D. Dimension D. And manifolds is another name for spaces. So the fundamental basic problem in topology is a classification problem. We want to classify spaces in some dimension, for example, in dimension 4. And the basic strategy to attack this problem is the construction of the invariance. Of invariance. That is, we attach to each manifold X some numbers or groups and so on. Ix, invariant of X. And so in order to classify manifold spaces, we have to distinguish them. So given manifold X and Y, we have to distinguish if X equal to Y or X is not equal to Y. So if Ix is equal to...
sorry, I cannot see. So you make some mark Ix to Ix. What is I and what is?
I is the abbreviation of I, invariant. now I'm explaining the basic
Data
idea
is
about
number.
environment. Huh?
Number.
Numbers, for example. So let me first give you some examples.
Number means, for example,
Z.
cohomology or
Yeah, Euler number. Let me give you some
Euler
examples.
number. Okay. I see.
Let me first give you some example. So just a moment. So for example, Euler numbers. So given a surface sigma, like this, with holes, then we get some number. For example, Euler number of sphere is equal to 2. And torus is equal to 0. So if chi sigma is not equal to chi sigma prime, then sigma is not equal to sigma prime. And using this invariant, we have a classification of all the surfaces, oriented surfaces. So the basic problem in topology is classification problem, and the basic strategy to attack this problem is the construction of invariants. So we want to construct many invariants. And in dimension 4, so D equal 4, we have Seiberg-Witten invariant. Which assigns to each for manifold X, 4-dimensional manifold, with, to be precise, with spin-C structure. But forget about this today. So anyway, to each 4 manifold, we get some numbers called Seiberg-Witten invariants. And the construction of this invariance the construction of Seiberg-Witten invariant is based on geometric analysis of Seiberg-Witten equations, some partial differential equations of geometric origin, geometric analysis of the Seiberg-Witten equation. Like this. The details of cyber-within invariance are not important, but this is a PDE, and in order to construct cyber-within invariant, we have to analyze this partial differential equation, and basically it is difficult. PDE of geometric origin. But in order to use this invariant, we have to compute the cyber-within invariance. But the construction is based on the very difficult partial differential equation method. It's difficult to compute cyber-within invariance. So one of the basic problems in cyber-within theory is give a combinatorial description of cyber-within invariance or more defined invariant, define the cyber-within invariance. For example, power for the invariant. Okay, and my problem today, my motivation today comes from this page, is very related, strongly related to this problem. And let me explain about it now. So I'd like to analyze, I'd like to give a cyber combinatorial description of cyber-within invariance, and cyber-within invariance is constructed from these partial differential equations. As I said to you, the detail of these equations are not important in this talk today, but let me tell you one thing. This is the Dirac equation. And my first attempt to attack this combinatory description problem, we are considering discrete Dirac equations as a first step to attack this problem. We are considering my goal today is to give a combinatorial description of power for the invariance, refine the cyber-within by discrete approximation of of the Seiberg-Witten equations. This is my strategy, ambitious strategy. And as a first step towards this problem, we are considering only this part, Dirac equations. We're considering discrete Dirac equation. And this leads to today's main theorem. I will show you again our main theorem. Today's main theorem is the analytic index of Dirac operator, the fundamental invariant of Dirac operator, can be computed by discrete lattice approximation of the Dirac operator, the Wilson Dirac operator. So this is a theorem about lattice gauge theory, but my motivation comes from topology. Then next, let's move on to the next topic, Wilson Dirac operator. So for any questions? Then let's move on to the discrete Dirac operators. Lattice operators. Before explaining lattice version, let me start with continuous version, continuous Dirac operators. Dirac operator, especially on tori. Dirac operators on torus. We denote it today by dcont because there are many Dirac operators in this talk. And dcont is defined to be gamma j times ddxj. And j is from 1 to d. And what is gamma j? Gamma j is called gamma matrices or generators of Clifford index algebras for mathematicians. And I will give you concrete examples shortly. Generators of Clifford algebras. And it satisfies the following three relations. First, gamma j is Q adjoint. I use mathematical conventions today. And gamma j squared is minus identity. This is also mathematical convention. And gamma j anti-commutes each other. Gamma I, j, gamma I. Gamma I, gamma j. Gamma j, gamma I is equal to 0 if I is not equal to j. And this is given by Pauli matrices. This is a generalization of Pauli matrices.
Wait. Could you show me again this one?
Yes.
So I'm slightly confused. This is commutator.
Anti-commutator.
Anti-commutator. In that case, I think this one must be plus.
Thank you very much.
I'm very surprised.
And thank you very much. Anti-commutator. E.g., in dimension 3, this is given by Pauli matrices. For example, And today we adopt this convention. I00 minus I sigma 2. But the details are not important, but anyway, I will show you my convention. I0. And in dimension 4, gamma 1, gamma 1, sigma 1 equal gamma 1, 2, gamma 3 is given by 4 by 4 matrices given by, for example, gamma 4 is equal to 0i minus 1. Oh, no. Minus 1. Oh, no. Okay. Then we call the product of gamma 1 times gamma 2 times gamma 3 times gamma 4. We denote it by epsilon. This is nothing but gamma 5 in physics. And epsilon is equal to 1001 minus 1. Okay, using gamma matrices, we have Dirac operators. And the most important, one of the most important relations for Dirac operator is anti-commuted relation with the epsilon. So D and epsilon anti-commutes. D cont is equal to del. And using this anti-commuted relations, we can define index of D to be trace of epsilon. Epsilon is gamma 1 times gamma D restricted to kernel of D. And this is using this relation, the Fredholm index of some part of D. Anyway, we can define index of D cont by using these anti-commuted relations. And this is a continuous version of Dirac operators. And we would like to introduce Dirac lattice operator, discrete approximation of Dirac operators. And what is approximation? Lattice Dirac operator on a regular lattice. And for fix some A positive and consider the regular lattice is at D on in RD. And for A, for phi, from this regular lattice to some vector space Cn, we define forward difference to be equal to phi x plus AEJ. What is EJ? EJ is a fundamental vector in direction xj minus phi x divided by A. So this is a very natural difference, lattice approximation of differential. And but we have another lattice approximation, backward lattice approximation. This is equal to be phi x minus AEJ over A. And the adjoint of DJ for F can be seen easily minus of dj b. So the sum is self-adjoint, and we define d to be gamma j times djf plus djb divided by 2. And this anti-commit with epsilon plus epsilon d is equal to 0. This is a lattice operator, but we have a bad news. This is not a good operator. This is not good. It's not a good operator. And we will consider, and this is called Nielsen-Ninomiya theorem. And this is closely related to Poincare-Hopf in topology. Theorem in topology. And this is a very fundamental problem. This is not good in the sense that, for example, index of this operator, we will call this naive Dirac operator. So this is called naive. Naive is always 0. And this is a fundamental problem. For odd order odd order partial differential operators. This is also known as red-black decoupling or even odd decoupling in numerical analysis. And thus we have to consider another operator, Wilson-Dirac operator. This is defined to be d Wilson is d naive plus epsilon grading operator times w. And what is w? And epsilon is grading operator. And what is w? W is Wilson operator, Wilson term. And defined to be w is wjf minus wj2. And d Wilson appears to be self-adjoint, but not anti-commit with epsilon. Wilson does not anti-commit with epsilon. So it's difficult to consider index, but it turns out this is a very good operator. And I'd like to give you one remark. This operator also appears in topological insulators, relation to top insulators. And in D equal 1, this is nothing but SSH model. And if D equal 2, this is not nothing but a Chern insulator. Chern insulator in class A. And D equals 3, This is class C operator. It's class C2. So it Wilson-Dirac operator also appears as in topological insulators. And it turns out this is very good for lattice Dirac operators, especially when we are considering analytic indices. Anyway, I would present you my main theorem again. For lattice approximation, we consider Wilson-Dirac operator. And as I said to you, D Wilson is self-adjoint, but it does not anti-commute with epsilon. So it's very difficult to define analytic index of D Wilson, but we define index of D Wilson to be the spectral flow of which I do not explain, spectral flow of D Wilson plus M epsilon. And M belongs to -1 to 1. And this is nothing but mass term. And we have two remarks. Index of D Wilson belongs to KO1 of I under I, and I is equal to -1, 1. And this is equal to Z. And index of D Wilson is also equal to the index of overlap fermions, which I do not explain, Dirac operator. And overlap Dirac operator is very closely related to Kaloubi's K-theory, which also appear in topological insulators, Kaloubi K-theory. And this is, I'd like to present my main theorem again. This is my main theorem. If we fix some data on the usual lattice, usual torus, and consider the lattice approximation of torus, and then the spectral flow of the Wilson-Dirac operator on the lattice, that is, we define this to be an index of Wilson-Dirac operator, is equal to the analytic index of the continuous Dirac operator on the torus. And moreover, the same is true for this index or family case, because we have used the proof, we use the K-theoretic method. The proof is based on direct computation in K-theory. And we do, especially we do not use Fujikawa method. Don't use Fujikawa method. In other words, heat kernel method. So our case-theoretic method can be easily generalized to Clifford indices or family case. And the key observation is a Wilson-Dirac operator satisfies a Gordon inequality, or in other words, elliptic estimate. But the naive Dirac operator does not satisfy the inequality. That's the key observation. And this is the end of my talk. Thank you very much.
Thank you for a nice talk. I have one maybe several questions. So, because your talk is rigorously organized, mathematically organized, but I could not find what kind of physical system you are considering. And I could not find any physical quantity, for example, and momentum and position operator or something, or energy.
Oh, this is a fermion.
Okay. I could understand that because you consider anti-commutator, so this is maybe a fermion, but I could obtain only that physical information.
Yeah, maybe.
What kind of fermion? There is so many kind of fermion, but we don't. Why you consider that kind of lattice system, and what kind of physical system?
So actually, this is not a quantum system.
Not a quantum system?
But yes, how to explain? So the lattice gauge theory is related to the regularization of path integral. So path integral is integral over infinite dimensional spaces. But so in order to define integral over infinite dimensional spaces, we need some regularization. And one method is using this lattice approximation. And using this this fair fermion, the Wilson fermion, Wilson Dirac operators, and the solution we can quantize this system.
I could not understand. So sometimes in the case of path integral, you consider Lagrangian somehow based on some integral, but there is no integral.
So there is no integral, so this is not quantized.
Quantized, but you consider under commutator, so it looks like a physical quantity.
So the Wilson fermion is a quantity that should be quantized.
Also, in the quantum systems, people consider Hilbert space and bounded operator on the Hilbert space. This is somehow one combination, but in the case of statistical mechanics and quantum field theory, people only consider operator algebras. For example, Konema algebra or sister algebra. Are you considering a kind of some operator algebra to describe quantum system?
I myself do not consider operator algebras, but and my motivation does not related to quantization problems. So I myself do not consider such systems.
So then I could find what kind of object you are considering in the context of physics or quantum theory?
Lattice gauge theory. Oh, actually, this is this main theorem is something related to anomaly. And when you consider the path integral, when you consider path integral, then in the determinant, the index appears, and this index is related to anomaly.
Yes, anomaly related to somehow quantum phenomena.
Yeah. when you consider.
But I could not find the relationship with some anomaly. Maybe you need to explain more physical system.
Maybe, but it's not for me, it's difficult to explain.
Difficult. Somehow anomaly is somehow very how to say a popular topic in SUSTech because the current president of SUSTech studied in that topic. I think this is true.
This is
true. Oh, something. But quite too mathematical, so I could not find its relationship.
Maybe as I said to you, this Wilson-Dirac operator is related to topological insulators. So this is directly related to quantum systems.
Maybe somebody, I will stop my comment or question. Do you have any comment or suggestion or question? I should stop my comments. So maybe other guy have some comment or question. For example, some relation with anomaly or something. Because I'm not so familiar anomaly, but somebody maybe more familiar to anomaly in the context of mathematical physics. I think there are several students with a background of mathematical physics. Somebody familiar that topic? Do you have any other question or comment? I think some of you have some questions because it's not so easy to understand everything. So okay, thank you.
Thank you very much.
Thank you, talk. Thank you very much. So maybe we need to proceed. Next speaker. So next speaker is who is? Maybe the session chair should be Professor Matsuo, and the next speaker is how to pronounce long issue from School of Science, West Lake University. But maybe Professor Matsuo should organize next session. So.
Thank you very much. I will chair the morning session. Next two talks. The next talk, Professor Shu. How do I pronounce your name correctly? Are you ready?
And they are younger guys, so maybe not professor, I think. Usually, short talk, the talk of speaker of short talk is not professor.
I see. But maybe Long Shu is not here yet.
She has some internet problem.
I see.
Please wait.
Okay. Thank you for the information.
Okay.
So just a moment. Then we will start the next talk 5 minutes later, 10:25 in China and 11:25 in Japan. Okay.
Hi.
Hi.
Oh,
Are you
sorry.
ready?
Yeah. There was some connection problems.
Sure. Then now I think you can share your slide.
Yeah.
By the way, how
What's
could you tell me how do I pronounce your name correctly?
Rongge.
Rongge. Thank you very much.
Yeah. So can you see my screen?
Yes.
So Rongge show your face.
Could you show?
Sorry.
Yes, please.
What is
Could
it?
you show your face? Please put on your video,
If possible.
if possible. This is usual. Usually, speaker should show your face.
What?
Do
I
you
should
have
show my
camera?
face. Okay.
You are very shy. Oh, thanks.
Oh,
Okay.
we can see your face. And could you show your slide again?
Okay. So shall I begin?
No, I don't. Nothing visible.
Okay.
Oh, very good. We can see your slide.
Yeah.
Are you ready
so
to start?
Yes.
Oh, the next speaker. So let's start the next talk. The next speaker is Ms. Longe Xu, and her title is Categorical Descriptions, One-Dimensional Gapped Phases with abelian on-site symmetries. Please start.
Okay. So I want to thank the organizers for inviting us here. And I think I'm the first student to present in Kong Liang's group. So since each of our students has just 20 minutes, when I was preparing the slides, I saw that instead of going directly into the details of our paper, which may be hard to follow, maybe I should first show the significance of this field and maybe lay some groundwork for other students in our group. And I should mention that this work is collaborated with Zhihao Zhang, and it is on archive now. So there is a famous saying by Eugene Wigner which states that mathematics is unreasonably effective in the natural sciences. What I want is to give you a feeling that among the fields of mathematics, category theory is somewhat unreasonably effective in the realm of many-body physics. And our paper is indeed inherited from this idea and will be used as an example to convince you later on. Before that, we may begin by revisiting the core concept in many-body systems, the phase. So I don't know the background of some of you guys, but I think you all have some senses about phase. We all encounter the phase transition about ice, water, and vapor every day, right? And people will accept that the phase of phase transition is a macroscopic phenomenon and should have a direct mathematical description for it. By direct, we mean to collect all observables in the long wavelength limit in a physical system and see what mathematical structure they form. However, for a long period of time, the pursuing of this structure has been put aside, especially for phases within long-dot paradigm. And it was partially because we did not have a clear language to approach it. So for the rest of the slides, I will show you how to find the observables in the lattice model and how to use categorical language to describe them. So we start from 1D. The small d means the space dimension, and later on, a big D will mean space-time dimension. So in a recent work, Kong Liang, Wen Xiaogang, and Zheng Hao use Ising chain to show that the macroscopic observables in a 1D gapped quantum phase form an enriched fusion category. By the way, in my opinion, this is a very important result. It tells us that even the most basic phases are not completely understood. And our paper is actually a generalization of the results. So if you have some physical background and are interested in this topic, I recommend you to read this paper. And this paper reveals that for a given 1D lattice model with a total Hilbert space H total, and for a Hamiltonian with local interactions, there are two kinds of observables in the long wavelength limit: topological sectors of operators and topological sectors of states. In the long wavelength limit, many degrees of freedom are not observables because there are always a lot of microscopic degrees of freedom, or to say the local operators surrounding a physical object. Observables should be things that are non-local and invariant under the action of these microscopic degrees of freedom so as to stand out. Therefore, the observables are the so-called topological sectors of operators or states instead of bare operators or states. So specifically speaking, the topological sectors of operators are the spaces of non-local unconfined operators that are invariant under the action of local operators. The sector consisting of only local operators is denoted by 1. A morphism between two sectors of operators is an operator that intertwines the action of local operators. Then the topological sectors of operators form a category denoted by B. Moreover, these operators can be composed and braided in 1+1D spacetime. So in consequence, the topological sectors of operators form a braided fusion category B. And the topological sectors of states are the topological defect lines, also known as topological excitations in 1+1D, which are the subspaces of H total that are invariant under the action of local operators. The sector generated by the ground state is called the vacuum sector. The topological defect lines can be mapped to each other or fused together, which indicates that the topological sectors of states form a fusion category denoted by S. Certainly, the topological sectors of operators act on those of states, which means that B should act on S. We denote the space of non-local operators which maps a sector of states A to another sector of states B by home AB. Then home AB should be an object in the topological sectors of operators B. This shows that the set of topological sectors of states along with the spaces of morphism home AB form a B-enriched category. Furthermore, the fusion behavior of non-local operators should be compatible with the fusion of topological sectors of states. Altogether, they form a B-enriched fusion category, S enriched in B, defined by a braided equivalence, B to Z1S, where Z1S is the monoidal center of S. And this B enriched in S is also called the topological skeleton, which is just what we want in describing the given phase of a lattice model. So maybe you are not familiar with the enriched fusion category. And And that's fine because speaker Zhihao Zhang, which is my co-author, will introduce more mathematical details about this concept in the afternoon. So moreover, a topological skeleton can be associated to different faces depending on what symmetry we assign. So in the presence of an on-site symmetry, we only consider sectors that are invariant under the action of symmetric local operators. So as an example, for a 1D symmetry protected topological order, or just a SPT phase with a finite on-site symmetry G, the topological excitations are symmetry charges, and they form a fusion category S equals rep G in the bosonic case. Therefore, the topological skeleton of a 1D SPT order with on-site symmetry G should be given by the enriched fusion category S enriched in Z1S for S equals rep G, obtained from a braided equivalence phi. So for the next few slides, I will use a 1D lattice model in our paper as a physical example to explicitly show that the macroscopic observables of the trivial SPT order indeed form rep G enriched in its monoidal center. In order to check the observables in a 1D SPT order, we construct a lattice model with abelian on-site G symmetry. So consider the 1D lattice with the total Hilbert space H total equals to the tensor product of HI. And each local Hilbert space HI is spanned by an orthonormal basis G, GI, for G belongs to a group G. And for each site I and G, we define an operator LG acting on HI as follows. So LG acting on HI will change the basis. And the global G symmetry is defined by UG, which is the tensor of LG on each side. And we also denote the set of equivalence class of irreducible representations of G by G hat. This G hat is the dual group of G. So for each side I and rho in G hat, we define another operator 0 acting on HI by like just reading out the basis of the eigenvalue of this basis. So, and let H be a subgroup of G. Note that G mod H hat can be naturally viewed as a subgroup of hat G. So for each side I, we define two Hermitian operators, the XH and the ZH. It is easy to verify that these operators mutually commute and are G-symmetric. Then we can define our Hamiltonian as follows as the equation 1. And this lattice model spontaneously breaks the G-symmetry to the subgroup H. And here is a remark. When G equals Z2, this Hamiltonian recovers the well-known 1D IC model. By taking different subgroups H in the Hamiltonian, we can realize different symmetry breaking phases. Here we just consider the trivial SPT phase. That is H equals G, and the Hamiltonian has just one term, the first term left. Now let us analyze the topological sectors of operators within this field, within this model. We can find two kinds of G-symmetric non-local operators, MG and E-rho, which are both a product of semi-infinite sites. So apparently the product MG E-rho is also a symmetric non-local operator. We use OG rho to denote the topological sector of operators generated by MG E-rho. Now we are about to show that OG rho is an object in braided fusion category Z1 rep G. We can calculate that if we change the place of E and M, they differ by a coefficient at most. So it follows that the fusion products of these topological sectors of operators are given by OG rho tensor OH sigma equals OGH rho sigma. And this recovers the fusion structure in Z1 rep G. Moreover, we can actually double braid the topological sector of operators by the following process. So for a site K between I and J, we can first create a pair of MG0 at sites I and J, then wind another MHE sigma around one of the sector. After this process, we annihilate the pair of MG rho we created as first and obtain a phase rho G sigma. It's the tuple, it's rho H sigma G. And this equation gives us a double braiding, so it's equation 3. And thus we show that the topological sectors of operators indeed form a braided fusion category equivalent to Z1 rep G. And now we show that the topological sectors of states of the SPT phase form fusion category rep G. So for the SPT Hamiltonian, the unique ground state is a product state. And MGI has only trivial action on the ground state for all sites I and G in group G. And we use S1 to denote the trivial topological sector of states generated by this ground state. So for each row in head G and site I, we define row I to be E row acting on this ground state. And we use S row to denote the topological sector of states generated by row I. Now consider this state, which is row I sigma J, defined by E row E sigma omega G. So intuitively, row I sigma J should generate the topological sector of states S row tensor S sigma, which is the fusion of S row and S sigma. On the other hand, by acting a local operator 0 dagger on this state, we find that row I sigma J generates the same topological sector of states as row sigma J. So it follows that the fusion rules of topological sector of states are given by S row tensor S sigma equals S row sigma. Therefore, topological sector of states form a fusion category equivalent to rep G. And since MGI only has trivial actions on the ground state, MG E row sigma -1 maps the topological sector S row to S sigma for all G in the group G. Thus, the home spaces between topological sectors of states are given by this equation 4. Hence, by carefully analyzing the observables in a lattice model, we prove that the topological skeleton of the 1D trivial SPD order with the bosonic on-site abelian symmetry G is the enriched fusion category, rep G enriched in its monoid center. And you may check our paper for more examples of the symmetry breaking phases to see the unifying power of the enriched categorical approach. So that's my talk. Thanks.
Thank you very much.
Okay.
Do you have any questions or comments?
So sorry, I have a question. So you consider that your group is abelian group?
Yes.
Oh.
But But this result does not care about a billion or not a billion.
Oh, I see.
But it's just my latest model is constructed to be a billion because I choose the simplest case.
Simplest case.
Yeah, of
So
the trivial
I
SPT
could
order.
not find why you consider that kind of model. You consider the product of some.
It's a generalization of the icing model, and the icing model has like two phases if we change the group. So so our model, we can
Aging model.
take,
Icing model.
yeah, take different subgroups and to realize different symmetry breaking phases. Yeah, and I just showed one phase. So yeah, and you can find more phases in our paper.
So in this situation, I mentioned that the one quantum system and the number you have so many I, so then you have so many particles. So you want to consider composite system. So in that situation, your group representation acting the same G in each side.
Yes.
Why we consider that kind of representation?
Why we consider this kind of representation? Because I want to show the symmetry protected topological order, and that is we have a G symmetry on each side.
Symmetric protected.
Yes, and it can realize symmetry breaking phases if we spontaneously break the group to its subgroups.
Of course, you are considering abelian group. In that case, irreducible space is only one dimensional. So, but you don't consider that kind of irreducible decomposition. Somehow slightly strange. So also you consider dual, so G hat. So usually considering a G hat, you can make irreducible decomposition of that given representation.
Yeah. Maybe.
But you
maybe I
did
should.
not consider that kind of decomposition.
I just showed one case, right? And maybe I should mention that this Z1 rep G is actually the quantum double model in 2D. If we use the unitary modular tensor category language. Maybe I didn't get your question.
So because once we consider that kind of irreducible representation, maybe we can make irreducible decomposition of that tensor product representation.
Yeah.
But you did not consider that kind of irreducible decomposition. Somehow, if you consider irreducible decomposition, what kind of state is invariant about that group? Can you understand? You have a group representation.
Yeah.
So then, tensor product. In that there is a tensor product system, and you have a so all G act on each system in the same way. So in that case, you can make irreducible decomposition.
Okay.
But you did not consider that irreducible decomposition. Once you consider irreducible decomposition, what kind of state is invariant about that group action?
I don't know.
I see. Okay.
Okay.
Any other questions or comments? Okay. Thank you very much again.
Okay, thanks.
The next talk will start 10:50 in China and 11:50 in Japan, 5 minutes later.
So maybe it is better to prepare next
Yeah.
speaker, I think.
Maybe I should share my screen now.
Yes, yes.
Please,
Okay, okay.
how do you pronounce your name correctly? Holibas Yang.
Yeah.
Thank you.
So can you see my screen now?
Yes.
Okay, okay.
Okay.
Okay, can you type your name in Chinese character? Maybe Yang is very common, Yang, I think, but I'm
Yeah.
not so familiar with Polybus.
Yeah, because in my Chinese name it's Shengyu. It's pronounced as Shengyu.
Sure.
Yeah, I translate it into English. Sheng means holy and Yu means universe. So I combine these two words to create an English name.
This is your English name. Okay.
I see.
Yeah.
Well, sometimes the Chinese name is quite hard to pronounce for European and Japanese person. So in this sense, many Chinese people often make an English name.
Yeah.
But in the case of Japanese, so usually Japanese name is not so difficult to pronounce. So then Japanese person has never has English name.
The reason why I choose this name is that I think my name has some meaning. If you just pronounce it, you cannot get that meaning.
I see. So sorry, your title is different from the original title of your talk. Your talk is Edge of the two-dimensional topological order, but now Edge of 2 plus 1D.
Yeah, the 2 plus 1D here is the space-time dimension. It's actually the 2D, 2 little d. Topological. Yeah, the 2 plus 1D means the 2 little d. If you only consider the spatial dimension, it's just 2.
Oh, I see.
Because if you consider something gapless, you need consider the temporal dimension. So in the title, I wrote the 2 plus 1D here for the space-time.
Oh, the time is coming. Are you ready to start, Holibas?
Yeah, I'm ready.
Yeah. Then next, let's start the next talk by Oliver Young, and his title is Gapless Edges of 2+1 capital D topological orders. Please start.
Okay. First, I would like to thank the organizer to invite me to speak here. Okay. This talk is based on the following 4 papers. The first 2 papers is a mathematical foundation of the Gapless edges, and the following 2 papers construct some important examples which describe the phase transitions. Okay. So many years after Wen Xiaogang introduced the notion of topological order, it has been well known that a 2+1D topological order can be described mathematically by a pair C and C, where big C is a so-called unitary modular tensor category, and the little c is a chiral central charge, such that the chiral central charge of the UMTC equals little c, mod 8. We will now introduce a complete mathematical definition of UMTC here. However, we will see the categorical structure of UMTC appears naturally in physics. For more details, one can read a note of topological orders written by Zhang and Kong. Okay, so for this picture, a 2+1D TO C0 admitting a gapped edge is called a non-chiral 2+1D TO. A non-chiral bulk might have several different gapped boundaries, such as L, M, and N. A 1+1D gap boundary is described by a unitary fusion category L. And a 2+1D TO has a gapped edge is equivalent to C that the bulk UMTC is the dream field center of a UFC. Then the central charge C of bulk UMTC must be 0. The dream field center in this picture is denoted by the ZL, ZM, and ZN of L, M, and N. If the gapped edge of a non-chiral 2+1D TO exists, then the following relation between the boundary and bulk was known. This theorem states that the 2+1D bulk phase is uniquely determined by the anomalous 1+1D TO on its boundary, and the UMTC C is given by the dream field center of the UFCL. That is, C is equivalent to ZL as braided as UMTC. Okay. Mathematically, different gapped edges L, M, N that share the same bulk or dream field center if and only if they are Morita equivalent as UFCs. Here's a remark. So there are counterexamples that a UMTC with 0 central charge cannot be a center of a UFC, which means a bulk TO with 0 central charge might not have a gap boundary. In physics, we might consider a Chen-Simons TQFT to construct such a counterexample. So above all, we have a complete mathematical description of gapped edges of a 2+1D TO. The natural question is whether there is a similar theory for gapless edges. In more details, we would ask, first, what is the mathematical description of a gapless edge of CC? Second, does the boundary bulk relation still hold for gapless edges? Third, what is the mathematical description of 0D gapless domain wall between 2 gapless 1D edges?
Sorry, I have a question. So what is a gapped edge and what is a gapless edge? What is a gap in this context?
I did not understand your question. Can you repeat again?
So you consider gapless edge and gapped edge.
Yeah.
So I could not find what is a gap in this context. Gapped edge and gapless edge. What is gap?
I think in this page I did not mention any gapped edge and gapless edge in detail. So I don't know. So I don't know how to answer your question.
But I want so but because sometimes the gap means that somehow the how to say incorrect word there is a somehow gap for the proof. But maybe this is different. Gap means that somehow step of proof is omitted. But maybe your meaning of gap is different.
Here the gap means that the energy the spectrum of energy is gapped. The gap is
particular energy. Okay, I understand.
Okay. Maybe I think it's
gapless means that continuous.
Yeah, it's continuous.
Okay, I understand.
Okay. In this paper, they prove that a bulk TO in any dimensions should be given by the center of its boundary, regardless whether the boundary is gapped or gapless, and whether the mathematical description of a gapless boundary is. It suggests us that the gapped and gapless edge of 2+1D TOs should be unified in a same mathematical language. Today's talk, we will give an answer of question 1. For question 2, the answer is yes. One can read more details in this paper and this paper. In the following talk of John, he will introduce the second work. For question 3, one can also read this paper. So if we consider a gapless edge at a fixed point in the sense of the long wavelength limit, the edge modes will be scale invariant and therefore also conformal invariant. So a gapless edge should be described by the data of a conformal field theory at that fixed point. We will only consider the unitary rational CFT here, which is described by a unitary rational vertex operator algebra. Roughly speaking, VOA consists of field operators as vector space and their operator product expansion as multiplication, which both respect the local conformal invariance, which is a versor algebra. In the following talk given by Kong, there will be more details of VOA and CFT. 2+1D non-necessary Carroll TO can have a Carroll gapless edge. The Carroll edge modes are states in a Carroll CFT with a central charge C. For example, the invertible TO has so-called E8H states. The corresponding Carroll CFT is the E8 level 1 WW model, which has only one trivial primary field. Also, a 2+1D TO can have a non-Carroll gapless edge whose edge modes corresponds to a non-Carroll CFT. A non-Carroll CFT is a tensor product of a Carroll CFT and an anti-Carroll CFT. An interesting example of a non-Carroll gapless edge is a gapless edge of the 2D Tori code. We will give a detailed description of this edge after we introduce a completely mathematical description of Carroll and non-Carroll gapless edges. So look at this picture. A Carroll gapless edge is given by the following data. The first is a so-called local quantum symmetry, V, which is a unitary rational VOA living in the 1+1D worksheet. So how to look at this picture is a 1+1D worksheet. The horizontal dimension is the temporal dimension. The horizontal axis is the temporal dimension. The vertical axis is the temporal dimension. Okay. And another data is a category B enriched in X enriched in B, which we also call the category of the topological defect lines. So its objects are levels A, B, C for each segment of line, which are also objects in X, and we will call X the underlying category. And there is a home space for each pairs of the objects, which will be denoted by MXY. And notice that MXY is an object of the mode V, which is the category of V modules. So that means the local quantum symmetry V can act on this defects. We will call B, which is equal to mode V, the background category. And there, for a category, there should be identity and composition. The identity delta X from V to MXX is induced by the V invariant condition, which means that we can transparently move on the 1+1D worksheet except 0D defect. That means you can act V to a line, that is MBB, from left and from right. The action will coincide. And the composition MYZ tensor MXY over V to MXZ is a morphism in mode V induced by an so-called intertraining operator, which represents the vertical fusion of 0D defects. Okay. Also, there is a monoidal structure. You can imagine that we can fuse the two topological defect line horizontally. Okay, so this is the monoidal structure. And there is also a unitary structure. So as a consequence, we conclude that here is the table. This should be X enriched in B. We conclude that X enriched in B is a mode V enriched unitary fusion category. We will denote a chiral gapless edge by a pair, V and X enriched in B. For more details of enriched unitary fusion categories and bootstrap analysis, you can read this paper. So if we set the background category of a gap domain wall M by the category H of finite dimensional Hilbert spaces, thus we can rewrite this domain wall as C M enriched in H. That means the local quantum symmetry of a gap domain wall is the complex number C. And of course, the rep of C is a Hilbert spaces. So mode C is equal to H. Therefore, gapped and chiral gapless domain wall can be unified in the enriched category language. Okay, so to construct a chiral gapless edge, note that for UMTC B, B enriched in B itself is a B enriched unitary fusion category. Hence, if B can be written as B equals to mode V for some unitary rational VOA V, we will get a chiral gapless edge V B enriched in B of the 2D TOBC. We have a so-called topological weak rotation to geometrically describe this gapless edge. So one can imagine that we first choose a trivial domain wall in B, which is a black line in the picture, and then flip one side from the spatial dimension to the temporal dimension. Then this temporal dimension with B is a chiral gapless edge of the 2 little debug. The chiral gapless edge construct like this is called the canonical construction. So using the topological weak rotation, we find a gapless edge is determined by the domain wall between the background category B and the 2D box C. So it is actually a BC bimodule. Then we have the classification theorem for all chiral gapless edges, which state that gapped and chiral gapless edges of a 2D topological order C are precisely described and classified by the pairs Vx enriched in B, where V is a local quantum symmetry, such that B equals mode V, and X is a closed fusion BC bimodules. Okay. So for non-chiral gapless edge, recall that a non-chiral CFT is a tensor product of chiral CFT and anti-chiral CFT. Let VL and VR be unitary rational values with central charge CL and CR, respectively, such that mod VL and mod VR are UMTCs. The following pair VL tensor VR bar over C and their representation category enriched in their representation category defines a so-called the canonical non-chiral Gapliss edge of this topological order, okay, which has central charge CL minus CR. We will call VL the chiral symmetry, VR bar the anti-chiral symmetry, and VL tensor VR bar over C the non-chiral symmetry. So in particular, VR and VR individual. So in this case, we will call the CFT the heterotic. If we set VL equals VR, then the central charge CL minus CR equals to 0. Okay. Here's an example of non-chiral Gapliss edge constructed from a chiral Gapliss edge by folding. The following figures describe this process. First, if we reverse the orientation of right side of circle, we will get an anti-chiral Gapliss edge V bar, X reverse enriched in B bar, which is shown in the second figure. Then fold the right side to the left side and squeeze together. We will get a non-chiral Gapliss edge, V tensor V bar over C, and X tensor X reverse enriched in B tensor B bar of the 2D topological order ZC0. Notice that when we doing the folding process, we will also need to squeeze the bulk together. So we get so the bulk now becomes to ZC, not C. Notice that there is also a gapped edge on the right side after folding. And we can prove that the center of gapless edge is ZC again, which is also the center of the gapped edge. So in some sense, it tells us the left side, which is the gapless edge, is equivalent to the right side, which is the gapped edge. So we will call such gapless edge gappable. Okay. Just like fusing gap domain walls between 2D tiles, we can also fuse a gap domain wall to a not necessarily chiral gapless edge to get a new one. In the case depicted on the figure, after fusion, the background category of new edge is B box times H, and the underlying category of new edge is a fusion of the underlying categories of the domain wall and the underlying category of the edge, which is B tensor M over B. And mathematically, you can prove it's equivalent to M. So for a more concrete example, let IS denote the async category, which is a module category of async VOA VS. We can construct a gappable non-chiral gapless edge for Z async 0 by the folding construction, which will give this gapless edge. So we also know that in the double async, there is a condensable algebra A such that the condensation of double async by A is a toric code. And there is a domain wall between them, denoted by Z async A, the category of red A modules in Z async. Then we can fuse this domain wall to the non-chiral gapless edge construct above along ZS and get a non-trivial non-chiral gapless edge of toric code, as shown below. So this gapless edge describes the critical point of phase transition of two gapped edges of toric code. So there are two gapped edges, which is one is rapidly 2, another is vectly 2. Okay. More generally, if we consider a Zn topological order, Z represents 0, we can also use the same procedure to construct a non-trivial non-chiral gapless edge. In this case, we consider the so-called power fermion VOA VPFN, and its module category Pfn. When n is old, we prove that there is a condensable algebra B in the double power fermion such that the condensation is ZNTO. Then after fusing the gap domain wall between double power fermion and the Zn topological order to the canonical non-chiral gapless edge, we will get the following non-trivial gapless edge, which also describes the critical point of the phase transition of completely symmetry breaking process of 1D gapped boundary of the NTO. So at least there are two gapped boundary of the NTO. One is Rapsian and another is Waxian. In particular, when n equals 2, the power fermion 2 is equal to Ising. So we get the previous result. In the end of the story, there is also a classification theorem of non-chiral gapless edges that is similar to the chiral case. Okay, so I will not read it because they are very similar. Notice that the chiral and non-chiral gapless edge can be unified together. If we cite the anti-chiral part of a full field algebra to be C, then we will get a chiral gapless edge. Moreover, recall that gapped and gapped edge can also be unified together in the language of enriched categories. So in some sense, we can see that almost everything is an enriched category. That's all. Thanks for listening.
Thank you very much.
Okay.
We are now open to questions and comments. Do you have any questions or comments?
Sorry, so I have one question. So you consider somehow gapless edge and gapped edge. So, however, I couldn't find some picture related to your edge. What kind of physical system you are considering? So you consider some edge. So, but I could not find what is your edge.
Sorry, there might be some interaction problem. I can't hear
so
you.
I cannot understand what is your edge. So the definition of edge was edge is somehow some point. What physical system you are considering? Please back to maybe first or second slide.
So which slides do you want to?
Where you firstly introduce edge.
H or age?
Edge, E-D-G-E. Edge.
Okay. When I see age, I mean the boundary of a block. Yeah. So
boundary of box.
Yeah, the boundary of a block. So if you know the toric code model, it have two different boundaries. One is a smooth boundary and one is a rough boundary. Just depends on how you cut the lattice. Yeah. So the boundary that boundary is the edge that I consider here. But they are both gapped edge. For gapless edge is it's a little bit to describe in lattice model, I think. You can because we are just consider using gapless edge to describe the critical point of the phase transition. Yeah. So if you want to see that, you can only consider the partition functions of the CFT. that will tell you some information from the lattice model.
Any other questions or comments? Okay. Then let's thank the speaker again. Thank you very much.
So I'll
And
finish.